And we've done quite a few arc length questions, so I'm just going to let them go, and hopefully you've had enough practice to do the rest. And the rest of 13.3 is our goal today. We are going to be looking at, got a whole bunch of people just turned up. Okay, this is not good. Okay, they're coming through now. It must be the internet's been a bit weird here. Right, focused on it. We are going to look at something called curvature, which we kind of talked about yesterday. And I'm going to do those first. And the questions that use curvature are 6 to 9. And then we're going to look at finding unit tangents, which we know how to do. Then unit normals, which is new. And finally, some unit binormals as well. And these are in questions 6, 7, 8, 10, and 11. So that's basically everything that's hopefully getting curved today. So let's remind you on a space curve. What does curvature look like? Well, at certain parts of a curve, say there, would you agree the curve's not very straight, not very curved? So it might have a kappa of, I don't know, 0.5. And then at this point here, it looks like a K, but it's actually, that is a symbol we use. And it's a Greek letter, as many math symbols are. And it's called kappa, right? So that's what I'm saying, if you're wondering what I'm saying. The kappa here could be 5, for instance. And we talked yesterday, I believe, that if you're a straight line, you get one kind of kappa, right? What was the kappa for a straight line? If a piece of a curve was just basically straight, what would its kappa value, its curvature be?
0.
0. Right, you can't get any less curved than straight, agreed? So kappa is 0. Bigger the kappa, the more curved it is. And we did the extreme, and remember, a single point in space technically would have a curvature of infinity. That's really not a question that you're going to be asked, but it is. And then all the other shapes have, you know, different kappas. A circle is quite interesting because in a circle, no matter what point you pick, right, the kappa is the same. So in this case, the kappa could be, I don't know, 4. So we are going to calculate this thing called curvature. Now, in a normal space curve, won't the curvature be different at different points? Right? It's not unreasonable to expect that. Now, there are some shapes, right, some curves, where the curvature is the same all the time. For instance, see if it was a little circle in 3D space where it was like orbiting like this, wouldn't kappa be the same number because it's a circle? Do you know there's another shape a little bit less obvious? I'll try and do it with my finger. But can you imagine a helix going upwards? Do you know on a helix, right, one of those looks like a spring? The kappa in those shapes is also the same at every point. It's curving the same amount. So what's the formula for calculating it? Well, there's a couple of formula, but the one we're going to use, that way we only need to remember one formula, is this one. This means the magnitude of the derivative of the unit tangent vector. And this is the magnitude of the derivative of the space curve R. And the first one I'm going to do is question 6. And we are going to find the curvature. And the space curve happens to be a helix. So what I'm going to do is I'm going to find the first derivative and then its magnitude. So let's do that. The derivative of this is 4. Derivative of this is -5 cosine t. The derivative of this is, sorry, -5 sine t. There we go. And the derivative of this is 5 cosine t. And the magnitude of the first derivative, because that's the guy that's going to go there, is the square root of 4 squared plus -5 sine t squared plus 5 cosine t squared. And that ends up being 16 plus 25 sine squared plus 25 cos squared. So far, so good. Now, most space curves, the curvature is a function of t, right? At t at one place, the curvature is 4, but t at a different place at 0, t at another place at 99, and so on. So it typically is a function of t, but let's see what it is in this case. Is there anything you can do to this expression, style points, that might make it simpler?
Factor out 25.
Okay. And you might not actually do this line, but I have. Do you recognize that sine squared plus cos squared is 1? So what you end up with is the square root of 16 plus 25, which is the square root of 41. So far, so good. Doesn't that mean I've now found that this guy in the bottom, right, this guy here, is the square root of 41. Are you happy about where that came from? Now we need to figure out this fella. I'm going to have to find the unit tangent vector. I'm then going to have to differentiate it and then find the magnitude of that thing. So there's a lot going on here. Now I'm going to use some stuff I already have. If you look back at one of my formulas, can you see that the formula for the unit tangent vector is the derivative divided by its magnitude? So in this case, we already know the derivative. It's 4 -5 sine t, 5 cosine t. So that's basically r dashed of t on the top. And it's to be divided by the magnitude of that guy. That's the formula for getting the unit tangent. So it's going to get divided by square root of 41. So the unit tangent vector is 4 over the square root of 41, comma, -5 over the square root of 41 sine t, comma, 5 over the square root of 41 cosine t. Are you happy about where the unit tangent came from? It's the first derivative divided by its length. First derivative divided by its length. Now, technically, couldn't I make some style point deals on that? I suggest you don't bother. Worry about the style points a little bit later. Let's just leave it as is. Now, I need to find its derivative, right? What will the derivative of 4 over the square root of 41 be?
Zero.
Yeah. I don't care what number it is. I don't even care how ugly that number is. Isn't the derivative of every number in the universe 0? Even 4 over root 41 is still 0. Right, now this fella here is just a multiple of sine. So when you differentiate it, won't you get the same multiple cosine t? And if you differentiate this multiple of cosine t, you will get negative the same multiple sine of t. So I've now got that guy. Now the top is the magnitude of that fella. So it's the square root of 0 squared plus this ugly guy, cosine t squared, plus this ugly guy, sine t squared. What does that get me? It gets me 0. That gets you 25, that gets you 41, and that gets you cos squared. So you're going to get 25 over 41 cos squared t plus 25 over 41 sine squared t. Are you happy about where the 25, 41s and all the other bits come from? We comfortable about what I did to get there? Now, if you're writing down what I'm doing right now, you know, you don't need to write, if you feel comfortable, every single line. You know, I put every line I can think of in. But if you think, yeah, I can go from there to there, I don't need the other 2 lines in, that's your choice. Okay. Is style points are now going to come in. Anything you can do with this?
Factor out the 25 over 41 and then cosine squared plus sine squared is equal to 1.
Right. So I'm putting in both lines, but like I said earlier, you may choose just to do that. So it's a number, which is nice. This question, the curvature is going to be a number, but in general, it's okay for the answer to be, you know, 5t squared plus 2, you know, things like that. It's okay to have t's in it. That will happen as well. Right. Is there anything style points that we could do with this guy?
We can take the square root of 25.
Are we happy about that? Now, let's put the package together then. 5 over root 41 goes in the top, square root of 41 goes in the bottom. Can I make that prettier? I mean, that's not a very pretty answer. Agreed? How could I fix it? Make it look nicer.
Becomes 5 over 41.
Well, let's find out if it does. It becomes this guy divided by that guy, which becomes this guy times its reciprocal. Of course, if you've seen that, you would just write that. Great, I'm just showing you why it is what it is. So for this space curve, the curvature is the same number all the time. And the reason for that is that it's a helix. And at any given point in that helix, can you see it's got the same kind of curvature? It's curving the same amount. Okay, it's curving upwards, but we don't care. It's 3D. Things in 3D curve up the way, they curve down the way, they curve sideways, right? We're not too interested in the orientation of the curvature, just that it's curved. Of course, there is a lot of work in that. We agree there's a lot of bits and pieces that have to be put together. And so that's going to slow you down. And, you know, that is what it is. So I'm now going to find another one. Which one shall I find? I really only want to do 2 of these because they take up so much time. Oh, God, yes, let's do this one. We are going to find the curvature of that guy. Okay, let's go through a little list. Just like the first question, I'm going to go through it the same way. I'm going to find the derivative. 4 root 2t gets you 4 root 2. E to the 4t gets you e to the 4t times anything else, if you differentiate it.
Times 4.
And same kind of idea, but -4 for the other one. Are we comfortable with that as the derivative? And now we're going to find the magnitude of that guy, because that's the guy that's going to go in the bottom, right? So we're getting that guy. It's going to be the square root of this guy squared plus this guy squared plus this guy squared. 4 root 2 times another 4 root 2 is 16 times 2, it's 32. This fella, boom, 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 gets you 16e to the 8t. Are you happy about e to the power of 8t? And that guy. Now, I'm going to rearrange these guys. The biggest answer, right, is that one. The middle is that one. And the smallest answer would be that one. If you made t 100, that would be biggest, that would be in the middle, and that would be tiny, right? So big to small. We are looking for style points. Help me out here. Style points. Anything you can do.
It's a perfect square.
Oh, you're going for perfect square. That'll work. How do you know it's a perfect square? Or what was the clue that it was going to be a perfect square?
There were 3 terms.
Yeah. Now, square root of this guy. 4e to the 4t. Are you happy about square root of 16 is 4 and half the power? Because the square root is basically half the power. Do we care about the number in the middle? No. We do the guy at the end. How we call that guy? Which means that this answer is that. So put a big bubble around it, make it easy to find. So we've got half the answer, don't we have the bottom bit? The bottom bit's going to be this. Great. So let's do the top bit. Well, I need to find the unit tangent vector. But I've already got half the work done. It's the derivative over that fella. And it's 4 root 2 e to the 4t -4 e to the -4t divided by this fella. So the unit tangent vector is going to be 4 root 2 of all of this guy this fella over that guy, and finally this fella over that guy. I can't just squeeze it in, it's that tiny. But this guy over him, this guy over him, and this guy over him. And that is only that bit. I am not going to do the next line. Can you tell why I am not going to do the next line? Don't you have 3 totally horrendous, ugly fractions to find derivatives for? So can we pretend we did it, we did it, we did it? Won't you then have to find the magnitude of that really ugly guy? Which is this guy squared plus whatever this guy squared is, plus whatever this guy squared is, and hope to heaven that it ends up being a perfect square that eventually comes out nice. And we just don't have time. It'd take me 15 minutes to do this question. And you're going to have to do it in your homework, so you might as well just bite the bullet. Are we okay that this would be a quotient rule, and you could probably do a quotient rule on that as well. And so that would be massive. And God, I'm cheating. I'm looking at the answer. There must be an awful lot of style points. Wow. So evidently, as ugly as this is, it kind of sorts itself out at the end. So go figure. So far, so good. Heavy duty algebra again, lots of differentiation, all kinds of fun stuff like that. One more curvature. This one is just a little different. We're going to find the curvature at a single point. All the other ones, you just found the curvature at any given value. This is going to be at just one place. Let's figure out how that is going to work. Pretty much not that much different. A little tweak at the end, it might look a little bit different, but that's about it. The derivative, 5, 2t, 3t squared. We're all happy with that? Magnitude, five squared, 2t squared, 3t squared squared. 25, 4t squared, 9t to the 4. Just checking that it might be a 3. No, it's not a perfect square, but it doesn't need to be, because we're only going to evaluate it at one point. What is the value of t that generates this point?
1.
Correct. How did you figure it out?
Because our y and z terms are both a z or a t squared. And
Okay,
the only
so
way to get 1
if-
from that is to have 1.
Yeah, like t cubed is 1, so t is 1. 5t is 5, so t is 1. There are different ways of getting it, but you got 1, right? Matching an x or y or whatever it is. So we are only interested in the value at 1. That is going to be the square root of 25 plus 4 lots of 1 squared plus 1 lots of 9 to the 4, which I believe is 4 and 9, 13, is the square root of 38. So I guess I'll stick it over here. The curvature at 1 is this fella at 1 divided by this fella at 1. Well, we already know the bottom guy, right? It's square root of 38. Don't I just need to know what this fella is and put that in there? Because this is evaluated at t equals 1, won't this be a number? I don't know what the number is yet, but I know it's going to be 1. So my unit tangent vector is this fella divided by this guy. And the derivative, I'm still having to keep it as t's right now, is 5, 2t, 3t squared. And the magnitude of this guy, I know in this particular case when it's 1, it's that, but it's going to be 25 plus 4t squared plus 9t to the 4. So you are going to have to take this ugly guy you're going to have to take this ugly guy, find his derivative, which I can tell you right now will probably be some massively ugly fella. You'll then find his magnitude, and whatever that number is, it'll go in there. These are not short questions. Which kind of makes it difficult to give you a test question in it. So you're getting tested by the homework questions in it, which in a way are a little bit better because can't you take as much time as you need and be as careful as you need. So do not expect in your test on Monday to be given this one. I could probably get away with a helix. Couldn't we do a helix because the numbers come out pretty easily? But not something as massively big and as ugly as this, or the one that came before this. They're for homework. They're for practice at the mega ones. Any questions about what we've got here? Although I haven't given you everything, but I've gave you like the crux of what you need to do, and you know you'd have to fill in the gaps. Are we good? Okay. You'll find out when you do homework, of course. So we are focusing on just one last guy. My green serum from my course. We're going to find unit tangents, unit normals, and in a couple of cases, a guy called the unit binormal. And the questions where that happens, I had a list of them. See if I can find it. Here we go. 6, 7, 8, 10, and 11, right? So there are 5 questions where you're asked to find some or all of those fellas. So let's look at what do we look at? Let's look at question 7. We are looking at 3t squared, the sine of t, take away t cosine t, and a cosine t plus a t sine t. And we're going to find, in this case, the unit tangent and then the unit normal. Do you recognize that the unit tangent, which is this guy here, is the same unit tangent fella that we calculated before? So when you're finding curvature, you've already found at least a third of the work that you're going to have to find anyway, right? So it's not, you don't need to reinvent the wheel, right? If you can say, oh, well, I already know what that is, I did it to find the curvature, you can just use it. But in this case, this is a brand new question, so we're going to have to do it from scratch. So that guy is 6t. This guy is a cosine of t, and then the derivative of this. And this guy is negative sine t, and I'm going to rewrite this because I didn't plan ahead. You don't need to write this, I'm just repeating everything again because I need more lines. Right, now I can do it. Differentiate 3t squared, you get 6t. Differentiate a sine, you get a cosine. Ah, our first hiccup. I need to differentiate negative t cosine t. Great. Make that f, make that g. Won't it be f dash g plus fg dash, because it's a product rule. That's negative 1 times cosine t minus t times negative sine t. And so you end up with negative cosine t plus t sine t. So you get negative cosine t plus t sine t. Come on. Now, if you differentiate a cosine, you get a negative sign. And if you differentiate t sine t, can you trust me that you get sine t plus t cosine t? Can you just trust me that's what you get? It's a product rule. Now, let's see if there are any nice style points going on. Well, that cancels out with that, and you get t sine t. And that cancels out with that, and you get t cosine t. Now, to get the unit tangent vector, we take this fella and we divide it by its magnitude. So it's 6t squared plus t sine t squared plus t cosine t squared. These are going to be massive questions. In fact, now I'm thinking about it, I think I might go back and knock a couple of questions off your homework, because once you've done 2 or 3 of these, you've done them all, right? They just take forever in the day to do. Right, so I'll remind myself when I leave to do that. This is 36t squared. This is t squared sine squared t. And this is t squared cos squared t. Let's look at style points. Is there anything you can do here that might make life easier?
Factor out the t squared.
Have you seen that sine squared plus cos squared seems to be a theme in quite a few questions? Won't that add up to, in this case, 1, which joined to that makes 37? Oh, wait a minute. Wouldn't it be even nicer to call it that? Agreed? And to get the unit tangent, which is what this whole thing was about, you divide the first derivative by its magnitude. And the first derivative is 6t, t sine t, and t cosine t. and it's going to be divided by that guy. So what do we get? We get 6t over the square root of 37t, t sine t over the square root of 37t, and t cosine t over the square root of 37t. And is there any style point thing that we could do here as well? You agree you can cancel a t? And so what do I get? I get 6 over this guy. I get sine t over this guy. And I get cosine t over this guy. And I think WebAssign is probably going to be quite generous about format, and it will take that. If it didn't take it, wouldn't you just rationalize the denominator in your second shot? So we have done half the question. We have found the unit tangent. So far, so good. Now, do you notice that the unit normal is pretty much the same formula, but you start with the tangent vector. So see all that stuff I just did? Can you imagine I just did it, but starting with this? So you just really kind of repeat the process. So what do? You find the derivative. 0. How about cosine t over the square root of 37? How about negative sine t over the square root of 37? Are you happy with the derivative? In fact, in a lot of ways, wasn't that derivative much easier to do? Now we find the magnitude of this fella. Well, it's going to be the nothing squared, that guy squared, and that guy squared. Oh, that came out quite nice, didn't it? In fact, leaving the square roots in the bottom kind of helped. Is there anything style points we can do to this square root that makes it nicer?
That cosine squared sine squared theme.
Right. So essentially, are you okay with that's what you eventually get? Right, that plus that is cos squared plus sine squared over 37, 1 over 37. And of course, style points means I can do that. Agreed?
Can you move your paper up just a tiny bit?
There we go. Does that help?
Yeah, definitely.
Okay, so the unit normal vector is the derivative of the unit tangent vector divided by its magnitude. And the unit tangent vector is this guy. That guy. And that guy. All divided by that guy. Right? Now, I'm running short of paper, so I'm going to do a couple of lines in one go. If you divide by this, isn't it the same as multiplying by the square root of 37?
Is it the unit tangent vector or the derivative of the unit tangent vector that we are using in the numerator?
It's the unit, it's the derivative of the unit tangent vector divided by the magnitude of the unit tangent vector.
Then you flip-flopped your...
Did I?
Yes.
Let's see what I did wrong.
Y and
the
Z.
unit, the unit thingy bobs. I did. I should have put a bubble around it. I looked at the wrong place. It's this guy. So what's that? A 0, a cosine t over this fella, and a negative sine t. Well, thanks for catching that. I just scanned up there when I should have scanned. Yeah. Okay, what's this guy going to come out as? Because he does come out really nicely.
0 cosine negative sine.
And you push that up. If you take this and do that, you get 0. If you take this fraction divided by that, the square roots of 37s essentially cancel out because you're going to multiply by root 37 and the 37 in the top and bottom go away. And the same thing happens here. Now, you don't get it in this question, but the 2 questions at the end do ask for the unit binormal. So let's pretend that this question wanted the unit binormal. Then what you would have to do is you'd have to take your answer to the unit tangent question. Which is this guy. I'm just writing it down so I don't scan the wrong one. This is the unit tangent vector. I have gone, haven't I gone and scanned? No, I've got it right this time. And the unit normal vector, which we just got a minute ago, which was what, 0 cosine and negative sine. Now, imagine you've already found those 2 guys, which we have. To get the unit binormal, do you know you just take the cross product of them? So you would go I, j, k, put in the unit tangent, which is this fella. Put in the unit normal, which is this fella. Let's see what we get then. So many i's, take away so many j's, oops, plus so many k's. If you go this way, you get negative sine squared over root 37. You go this way, you get negative cos squared over root 37. That ends up being negative 1 over the square root of 37, because sine squared plus cos squared trick. If you do this one, you just get a negative 6 over the square root of 37 sine d. And if you do this one, you only get that guy because this is 0. So you get a 6 over square root of 37 cosine t. And that becomes this fella, positive this fella, and positive this fella. Whew. That was a lot of work. Unit tangent, unit normal, unit binormal. So for the last few moments,
for the first part, you have cosine squared t minus sine squared t.
Oh, you want me to check that first one again? I have minus this guy, minus that guy.
Oh, minus. Okay, you're right.
Okay,
I
but
forgot
worth
about the
checking.
subtraction part.
Yeah. I'd rather you got me to check because, strange as it may seem, I have been known not to do it right. So I want to show you something in the last few moments about what on earth are we calculating? Because right now you're just doing a whole load of work to find 3 things called unit normal, binormal, and tangent, right? The analogy of the roller coaster kind of works well with what I'm about to show you. As you're traveling along a twisty corkscrew roller coaster, there's actually 3 forces that work in unison that describe what's happening to this moving object. Let's just pick that point there. You know the vector that shoots you off to your death? Well, the unit tangent is pointing in that direction. Now, if you're on a roller coaster, do you know when you go round a bend, isn't there a force that makes you go towards the center of the curve? And that guy there points in this direction, and that's what your unit normal is telling you. The direction that is in the curvature, is it called centrifugal force or something nowadays? Right. Now, when you're in a roller coaster, you've got that shooting forward, right, which is the T, the coming round the corner, which kind of pushes you into the side, right? But don't you sometimes also get the lifted out of your seat one? And the lifted out of your seat is the binormal one. So those three, unit tangent, normal, and binormal, what they do is that they describe the three, and they're all perpendicular to each other, which is interesting, right? They're all at right angles to each other. And those three vectors represent the direction of those three forces, right? The forward force, the curvature force, and the G force. For instance, do you know, because I know this because I've seen it, that you can go up in a big aircraft, and they do it with astronauts, and don't they do a special loop on the aircraft that makes you weightless? You ever seen it? Where they're on the aircraft and they get this kind of, it's to try and emulate what weightlessness in space is. A lot of space astronauts get training on this. What they're doing there is that they're doing a controlled spiral that has the upward force, right, the one that's lifting out of the seat, quite large. And if it's large enough, won't it feel like you're weightless? So that's essentially, so if you saw the aircraft, you never do, but if you saw the aircraft from the outside, it would either be maybe not a complete helix, but it might only be this piece of the helix, right? It would be one very long, deep curve towards the Earth that would try and generate the upward force that would make you feel gravity. You know, if they do it the other way around, don't you feel like you're being pushed into your seat? Jet pilots exhibit those three forces to quite big extremes, right? You know, G force is basically the binormal force, right? Sometimes it's pushing them into their chair, right? And it makes it hard for their heart to work because it's fighting extra gravity. Sometimes it makes them lightheaded because you're going the other way and you feel almost weightless. You know, if you're in a jet, not I've ever been in one, but if you're in a fighter jet, you know, 3G or something would be a painful place to be. So I don't know if that makes you feel better about all the hard work, but does it at least give you an idea of why you might want to find those three guys for a space car, right? They at least tell you something that is useful. And say hi and bye-bye. I'll see you tomorrow. We learned some cool stuff today, guys. Right? We learned how to tell the binormal force or the vector as you shoot off to your death. Oh, we got a lot of customers today. Who's got the first question then? Are you just hanging about, Emma? You want to listen to other people's questions? Some people do that. That's okay if you want to.
No, I really have some problems.
Okay, give me your question first, and then we'll just work our way through the gang.
Okay, well, can we go back to what we just did in class?
Well, yes, I'm going to have to pick it out, but here goes. I got it, I think. What is it you want to go over?
So can we
And please don't say the whole thing.
can we go with the cross product, please? Because I don't
Can we
get
go over what again?
the cross product.
Oh, yeah, the cross product guy. Here we
Yeah.
go.
I think you just have to talk me through it because I really don't get it.
Okay, so what we're going to do, oops. We've already found the unit tangent and the unit normal. To get what's called the unit binormal, what we need to do now, oops, flip this over, is the cross product of these two vectors. Now, t goes first, cross product with n. T goes here, n goes here. So far, so good. Now, normally when you do cross products, isn't everything just numbers and, you do what you do? I'm not going to do anything different. It's still the same rule. It's just that there's going to be some t's as well as just numbers. So here goes each one. If I'll hide this and pretend I was doing it from scratch. So the unit binormal, it's so many i's, take away so many j's, plus so many k's. Agreed? Now you cover up the i's. Let's see what we get. If you go this way, you're going to get negative sine squared t over the square root of 37. Take away cos squared t.
Shouldn't there be a negative cosine for the k on the top, or no?
Okay, this.
Yeah, if you look at your original function.
Did I write this down wrong? Positive, 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 0, positive, negative. Are you saying that this should be a negative, Douglas? Is that what you're saying?
Yeah, the cosine.
Let me check if it was a negative in the original.
Oh wait, never mind. I don't think it was. I just
okay,
looked at it.
right, we're
That was
good.
my mistake. Yeah.
No problem. Right. Okay, so back to this fella. Major, take away minor. Now, do you notice that they share a root 37 on the bottom? And if you pull out a negative, I don't know if this helps, but can you see that it's basically just negative 1 over the square root of 37? Is that good? Right. So negative 1 over the square root of 37. That's that one done. Now, if you cover up the middle one, the major diagonal is this, take away 0. So all you're left with is a negative 6 root 37 sine t. And the last one, major diagonal, take away nothing. That's going to leave you with 6 over the square root of 37 cosine t. And if you take this guy, what do you get? You have this fella. And that becomes a positive now. And this fella. Are we good? Is that what you needed to see?
Yes, my brain was not accepting that.
But it's accepting it now. Okay, that's good. Who's got the next question? We'll kind of do one from each person until they're used up. Have we got any more questions?
I'm a spectator as usual.
Okay.
I'm just a spectator.
Right, if that's it then, the show is over, guys.
Well, if
I'll
they don't have any questions, I'm going to use up more time.
Oh, go for it. I didn't. Hey.
I actually do.
Okay, well, let's do you one. Ivan, what's your question? Then I'll go back to Emma for the next one.
I actually had a question about
about the homework on
Mhm.
13.1 and on number 14, I just got really confused. I didn't know what I was looking at.
Okay, let me. I think is it an easy question, or shall I pull it up? Is it something you can write? Tell me relatively quickly or not? I'm on it now anyway, so here goes. 13.1 question. Oh, it's the second last question. So what are we looking at here? Yeah, I remember this question. We had this is exactly the same question that James had yesterday, but we'll show you. This is t squared, t cubed, and what they should have done, but they didn't, is that they should have used a different variable for the second curve. So I'm just using the ones that are in front of me. That way I know they're going to come out. That there is a 1. Now, they had t's here. And what I did wrong, and what you probably did wrong as well, is that if you make everything t, you just match the x's, you match the y's, and you match the z's, and nothing fits. To which the question doesn't work, right? You can't make it work. So if you change the variable names, matching the x's gives me that, right? I'll call that equation 1. And if you match the y's, you get that. We'll call that equation 2. Now, if I use this fella here and I substitute the t with this fella, I can now get 1 plus 2s, because that's what t is, squared, is 1 plus 6s. And that's 1 plus 4s plus 4s squared. And that's what? 4s squared, take away 2s equals 0. And once you subtract things from both sides, pull out, well, you could pull out more than that, pull out 2s, and you get 2s minus 1. And that gives me two solutions. It gives me s equals 0, and it gives me s equals, well, in this case, a half now. So far, so good. Now, for s equals 0, t will be 1. And I just did it by plugging in here. For s equals a half, t will be 2. Now, if I use s equals 0 or t equals 1, if you plug it in here or you plug it in here, you'll get the same coordinates. So let's just plug s equals 0 in. And the answer that you get, right, is 1, 1, 1. So that counts as one of the points where the two curves essentially cross each other. If you then go to the second one, which is this one here, if you plug in s or t, it doesn't matter, you'll get the same coordinate in both cases. You'll get 2, 4, and 8. So essentially, there are two places where these curves meet. That might be R1, and it goes, it goes like this, and then R2 looks like this fella. And what we found are the coordinates 1, 1, 1, which is for this one, and the coordinates 2, 4, 8, which is for this one. And that's what they talk about, the larger and smaller x's. I'm just going to complain. They should have called it R2 of S, and it wouldn't have been such a big deal. Now, find the times when the particles collide. Enter your answer, and if it doesn't exist, then you do DNE. Now, if you make this T again, and you match them up, you'll find that these two guys don't reach the same point at the same time. And so it's a DNE. Is that what you're looking for?
Yeah, I think the majority of why I got confused was because they had two T's instead of an S.
Yeah. I agree with you. That was a bad. WebAssign's
So-
to blame, not you, for that one. They could have set it up in a way that would have made it clearer, the process that you need. Right, you're on, Emma. What you got?
Okay, so this is going back to Calc 2. It's a baby question, so it shouldn't.
I like baby questions because I can maybe get them right. So go for it.
Okay, it's the integral from 0 to 1 of the square root of 4t squared plus 9t4.
Okay, that guy?
Yep.
Okay. It's not a perfect square. How do I know it's not a perfect square, which is what you would hope it was? How do I know that that is not a perfect square?
Because there's not 3 terms.
Correct. So, ain't going to happen. So what have I got left with? Well, you do what you do. You look for something else. Can you see anything you could do with 4t squared plus 9t to the 4? Anything algebraic?
Okay, the only thing I can see is pulling out a t squared.
And that is exactly what you should have done. Now, when you do a square root, can't you do a square root of each one separately? In other words, it now becomes this guy. Agreed? Square root of t squared gets you t. Now, how do you think you're going to solve this guy?
That's a u sub.
Yeah. And won't the u sub be 4 plus 9t squared? Is that enough of a clue you'd be able to finish off now? Or do you want me to keep going?
Please keep going.
Keep going. Okay. So you differentiate with respect to t, and you get 18t. You do the crossover, and you get 18t dt. And you isolate. So remove the limits of integration for a little while. T square root of u 1 over 18t du. The t's cancel, and you're looking at that guy. Now that guy we can integrate because we can write him as u to the half. I can then add 1 to the power and divide by 3 halves, which is the same as multiplying by 2/3, which I believe gets me 1/27. That in turn becomes that guy. That's what 3 halves looks like if you put it in a square root. That in turn becomes this fella, which we will now evaluate at t equals 0 and t equals 1. If you plug in 1, you get 1/27th, the square root of 13 cubed. And if you plug in 0, you get the square root of 4 cubed. And the square root of 13 cubed gets you 13 root 13. And the square root of 4 is 2, and 2 cubed gets you 8, so you get 8. And if you pull out 1/27, you get 13 root 13 take away 8. And that's what it would look like.
Thank you.
Okay, any other questions, guys?
I have a question.
Yes, what you got, David?
So I'm struggling a bit to understand how the normal vector gets that vector that you showed before, where it's perpendicular to the
Yeah, so
tangent vector.
yeah, you got your thing going like this, and I was saying something along the lines of if you choose a point, are you happy about the unit tangent? Basically, that's the direction of the tangent line, right? That's the way you shoot off to your death.
Yeah, and then
Yeah.
the binomial vector being the cross product being perpendicular going in the opposite direction also makes sense.
Right, it's just
literally
why is that?
Yeah.
Why is that at right angles to T?
Yeah,
And because intuitively to you, there's no reason it should be, right?
because it's just a derivative of it. Yeah.
Right. So let's isolate the question. Imagine that was a blown up version of what's going on. And can you imagine a tangent line? And I'm drawing it longer than it needs to be, going this way, right? Isn't this very circular?
Yeah.
If you do something at right angles to a circle, do you see that you get that other direction? Do you see it just naturally follows?
Yeah.
That's kind of the reasoning behind it. Although that doesn't look like a circle, for very, very, if you zoom right in, isn't every curve a bit circular eventually? Unconnected with that, but kind of interesting in its own right. Do you know if you find kappa here and it ends up being 4, and you're wondering, you know, how can I use that 4 to get a feel for how curved it is? If you do that little right angle guy, basically there's a circle here. And the radius of that circle is 1 over kappa. So if kappa is really big, right, can you see that the circle will have a very small radius and therefore be very curved? And if kappa is tiny, like 0.1, won't the radius be 10? And it's a big, slowly curving circle. So kappa is a measure of a circle that would have the same curvature as your curve.
Okay, that makes sense.
So if you're thinking where it's coming from, so you see this guy here?
Mm-hmm.
The circle that would make, that's not really the center, there's the center. That guy there, right, is the circle that would be 1 over it, right, would be kappa.
Okay.
So the unit normal does have a connection to the circle. If you imagine at any point in a curve, it behaves like a bit of a circle. And 1 is the tangent line. Won't the other force be at right angles? Because on a circle, if you have a center and a tangent line, isn't the line joining the center to the tangent line always at right angles to the tangent line?
Okay.
And that's kind of where it comes from.
That makes sense.
Okay, good. An interesting question. I don't normally get people to do that. A lot of things in the higher level of math take some conceptual leaps. You know, it's hard to think in 3D when you've spent your entire math life thinking 2D, right?
Yeah.
And so, you know, it's to be expected. Now, if